Hello ladies and gentlemen, and welcome back to GGS 300 Quantitative Methods for Spatial Science. Today we're going to be focusing on the 8th lecture, and the topic for this week is Inferential Statistics and Hypothesis Testing, Classical Hypothesis Testing. So where are we? Well, you've hopefully all handed in the 5th assignment today, and that will mean that today I'll also set the 6th assignment, which will be due on October the 21st, so 7 days from now. So don't hesitate to reach out to me if you've got any queries or questions on the work that we're going to be carrying out. I think this week it's a reasonably straightforward piece of work, and I think today is going to be a reasonably short lecture, and then obviously in the lab work we'll go through testing some of these hypotheses using some kind of quite simple statistical tests, which we're going to go through in the second part of this lecture today. So without much further ado, I'm going to progress, and we're going to actually dig into this content on inferential statistics and hypothesis testing, so kind of moving on to the second part of the kind of overall course. Okay, so it's actually the second third, but really we're focusing now very much within this kind of this box diagram, which I've presented you many times, as kind of the second part over here. Okay, so we did all of that work on descriptive statistics in the first third of the course, and now we're actually focusing on formulating hypotheses and then actually testing them after collecting samples of data about our population, evaluating those hypotheses in a formal statistical way, and then actually either developing further theory or the model, or hopefully, ideally, in a best case scenario, going out and actually gaining impact from these models that we've developed, so actually influencing real world decisions in industry and government, and that's what I hope you all go on to do with this work. So, hypothesis testing, what is it? What are we doing with it? So essentially this is a method of statistical inference. Well, okay, fine, you might then ask, well, what exactly is a hypothesis? And you can go and look this up in the Oxford English Dictionary if you would like, but essentially this is a statement that we're going to make about how we think the world works that either needs to be verified or shown to be false, okay? So often hypothesis testing is actually used with those sample statistics that we might collect, those sample statistics which we might apply to a sample which we've collected. So that could be focusing on things like the mean or the standard deviation, for example, as we've covered in previous lectures. And then we use that to actually determine if we have enough evidence to draw some sort of conclusive statement about the world, okay? We can never be 100% conclusive, but we can often be 90 or 95% certain that the conclusion which we're drawing about this hypothesis could be true. Okay, so it's quite hard to get, it's quite hard to find definitive truth in the world, but it is possible for us to make quite substantive statements about the world based on some data that we collect and then we analyze and formally test. So I'm going to cover quickly hypothesis testing, so these basic 6 steps which are outlined within the book, and then essentially we're going to look at some tests that we can apply in the second part of the lecture, and then as we move on through the term we will be using p-values, so probability values essentially, which reflect this kind of 6 steps that we're going to be covering here, but in a more a more simplified way, okay? So this is, when we look at a p-value, as we will do later, it will reflect these 6 steps that we're going to take here. But as we get into the more complex part of the course, we won't be going through all of these 6 steps, we'll just understand what a p-value is, okay? So the first part here, we're going to be covering these 6 different steps, and hopefully that will then become kind of clear as to exactly what we're doing here, okay? So we're focusing on how we accept or reject the hypothesis that we've made based on a level of significance, and that level of significance is going to be based on the alpha value, which is going to be somewhat familiar to you because we covered the alpha value in the previous lecture when we focused on confidence intervals. And ultimately this is going to be a binary decision, okay, so it's going to be an accept or a reject based on the outcome that we have from our statistical test. There's only 2 potential outcomes, okay, and we're going to divide our probability distribution of the normal distribution into segments so that we have a very clear accept and reject part of the distribution based on probability, which informs our kind of formal conclusions regarding that hypothesis. So there's 6 different steps here. So we're going to state the null alternative hypothesis first before we actually start looking at data. Then we're going to actually select the appropriate statistical test, define a level of significance that's acceptable to us, because obviously there's going to be an element of error within that, and that's going to be very much subjective on the problem. We'll then delineate regions of rejection and non-rejection of the null hypothesis, calculate the test statistics, and then make a decision regarding that null hypothesis. So how do we state this null alternative hypothesis? Well, the standard status quo is always going to be the null hypothesis, and that's where we assume there's no relationship between the things that we are going to be analysing. Okay, so let's use a classic example that Ed likes to use. So let's think about the property prices in Fairfax City in relation to the property prices in the whole of Virginia. Okay, so let's use an example of the whole of Virginia being the population, so the mean property price across the whole of the state, and then let's use a hypothesized sample mean where we go out and we collect mean house prices for Fairfax, okay, just the city area, which will be the sample. Essentially then we would categorize the null hypothesis as there being no difference between this sample and the population. Okay, so basically you have the population mean here, and it's equal to the mean of the sample that we've just collected, and that's this H0 here, the null hypothesis. Okay, so we're saying that the population is equal to the sample. And then that contrasts with the alternative hypothesis, this HA, so that's where we assume that they are actually quite significantly different. So this is where the population mean is not equal to the sample mean. Okay. Now we can state these alternative hypotheses in different ways. So we could have a directional hypothesis, so that's basically where we would say that the property prices in our sample, this mu h here, so in Fairfax, are actually higher than the rest in the state of Virginia, this mu value here. Or we could state it the other way, so basically say that we think that the population mean property price here for the state of Virginia is actually higher than the sample for Fairfax City that we've collected. Okay, so that's known as directional because we're saying whether something is larger or smaller than the population. In contrast, we could just have a non-directional two-sided alternative hypothesis, and this is basically where we say that we think they're different, the mean property price in Virginia and the mean property price in our sample for Fairfax, but we're not going to say whether one is larger than the other, we're just going to say they're different. And this matters because when we get to actually dividing our normal distribution, it's going to affect where that alpha value is basically distributed. So in a directional, we would have all of that alpha value distributed at one end of the distribution, whereas if we said it was non-directional, we would basically have to split that alpha value into each end of the distribution because we're not actually making an explicit, we're not explicitly saying whether we think it's smaller or larger, okay, and therefore which part of the distribution it's in. So what we're doing here is we're testing whether or not we think the null is true, and the null is always the de facto approach that we have, and that's basically where we think there's no difference between these two things. All right. So the null hypothesis here is that there's no difference between the mean house prices in Fairfax and the rest of Virginia, whereas the alternative hypothesis is that there is a significant difference between the house prices in Fairfax and Virginia. Okay. So then we need to select appropriate statistical tests. So in this case, this is going to depend on the type of question which we're actually going to ask, and also whether we can meet the particular assumptions of a statistical test, and I'll keep coming back to that as we go through this course. So we're going to discuss today the one sample difference of means test, as well as the one sample difference of proportions. So they're basically quite similar, these tests, but one we have a continuous mean and one we have a proportion of an overall sample. Okay. Now, we want to be as specific as possible when we identify these tests, and it's going to be important, for example, when you carry these out and you report what you've done, for example, in your dissertation research, that you're very clear that maybe you used a one-tailed, one-sample difference of mean test using the z-score, okay, using the z-distribution. And that's important so that people reviewing your work know exactly what you did, and then ideally can actually reproduce those results. We then need to select the level of significance for our test. So we know that the significance level is the alpha value, so that could be 0.05 if we want to be 95% certain, or it could be 0.1 if we want to be 90% certain. And essentially the significance level is also known as the likelihood of you committing a type 1 error. And then you're going to obviously ask, well, what's a type 1 error? And unfortunately, you're just going to need to learn that there are these different types of errors that we can produce. Okay, so a type 1 error essentially is when we see a false positive. So this occurs when we reject the null hypothesis, but the null hypothesis is actually true. And then that contrasts with a type 2 error, where basically this is a false negative. So this occurs when we don't reject the null hypothesis, but the null hypothesis is actually false, okay? So if we have these two different axes over here, so this is truth, so the null hypothesis being true and the alternative hypothesis being true, and then the research outcomes here, so the null hypothesis being true and the alternative hypothesis being true. And obviously, if the null hypothesis is true in reality and our research then confirms that the null hypothesis is true, then we know that we're in a good place, so this is accurate. And the same goes if we have the alternative hypothesis being true and the research suggesting that the alternative hypothesis being true is true, then we're also in a good place, okay? So we're in the bottom right quadrant here of the graph. Now the problem occurs when basically the null hypothesis is true, but the alternative hypothesis is identified by the research as being true, because that's actually a type 1 error, okay? So this is a false positive that we're seeing. This is very bad. And then equally, if the alternative hypothesis is true, but the research suggests that the null hypothesis is true, then we get a type 2 error. And this is bad, but it's not quite as bad as a type 1 error. And the reason why there's a difference there is, for example, in medicine, if you're deciding if someone potentially has a certain type of cancer, then actually it's very bad for you to think that to get a false positive, basically, because what you're going to do is you're going to subject somebody to a treatment that will also potentially be detrimental to their health. So, for example, chemotherapy is incredibly traumatic on your health, but it's often better to go through that process than let the cancer spread to the other parts of your body, for example. And obviously, if somebody doesn't actually have a cancerous tumour, for example, then it would be very bad to subject them to that type of therapy. So it's almost better to make a type 2 error than it is to make a type 1 error, okay? So step 4, let's delineate the areas of rejection and non-rejection. So this basically goes back, it's very similar to how we defined those confidence intervals previously, but this time we're doing it based on a hypothesis testing approach. So the area of rejection can be related to whether we had a two-tailed non-directional hypothesis, because then the alpha value is going to be split at both ends of the tails, or whether we had a one-tailed directional hypothesis where we think that the sample is going to be explicitly larger or explicitly smaller, depending on how we think the world works, than the actual population, and therefore the alpha value would just be at one part of the distribution. So we need to identify the critical value using either the Z or the T distribution, so depending on the number of samples that we've got. Obviously, if we've got lots of samples, then we'd use the Z. If we've got a small sample size, then basically we'd use the T distribution. And essentially what we need to do is, for a one-tailed directional distribution, we can find the Z associated with that alpha value, and that would be like this case 2 over here. So we would have the alpha value just distributed at this point in the upper part of the distribution. So this, for example, would be like us saying that we think the house prices in Fairfax are going to be larger than the state mean house price, okay? And we want to be 95% certain in that hypothesis, and therefore we have 5% error margin, which is our alpha value, which is going to be in the upper part of the distribution here. And we're going to need to basically find the point at which this line sits in the standardized distribution. And we could do that using Q norm, for example, in R, as you did in some of the previous tests. So you would give it Q norm, open bracket, 0.95, and then that would basically spit out that it's 1.65 standard deviations above the mean here, providing you tell Q norm that it's for a one-tailed hypothesis, and therefore you need to make sure you specify which part of the distribution it's in, but it would basically produce this delineation, okay? So we know if we find a mean that sits in this upper part here, we would reject the null hypothesis because we'd be 95% certain that the sample that we've got is different from the population, it's larger, Whereas if the actual mean for the sample was in this area here, then we wouldn't reject the null hypothesis because we don't have enough evidence to suggest that the mean house price in Fairfax is actually larger than the rest of the population based on the alpha value that we've specified, okay? So look, don't worry, we'll get to more of that in this class, but essentially that's how you do this for a one-tailed directional format. And then you can do the same over here, it's just that you're going to take your alpha value and divide it by 2. So if we want to be 95% certain, then basically our alpha value of 0.5 will be divided by 2, which means we get 2.5% in the bottom and the upper part of the distribution. So that would be 0.025 down here and 0.025 up here as the probabilities, as all of the probabilities here add up to 1. So we need to find this value here, and it would be 1.96 standard deviations above the mean to find this line, and it would be minus 1.96 standard deviations below the mean to find this line here. Okay, so then we would calculate the test statistic once we actually delineated those rejection regions or acceptance regions. And it would depend on the test, so we'll cover this shortly, but basically we'll calculate the sample statistic to calculate, we'll use the sample statistic to calculate the test statistic. And those test statistics are going to be based on either the z or the t values, predominantly, at least for the way that we're approaching this here. And then we need to make a decision regarding the null hypothesis. So I already touched on this in the previous two steps ago when we delineated the regions, and I kind of gave you a little bit of a thought, process for how we make this decision. But essentially, if the calculated test statistic falls in the area of rejection for the null hypothesis, then we would reject the null hypothesis based on that confidence level. And there's a very kind of specific way that you need to say this, all right? So we basically need to say that we reject the null hypothesis of house prices in Fairfax being the same as the population of Virginia, so the mean house price for Virginia, with 95% confidence, and conclude that the alternative hypothesis of the house prices in Fairfax City being larger than the state of Virginia is true. Okay, so obviously I kind of ad-libbed in there the different different kind of points that we kind of took from those examples before, but you get the point, right? Which is that we have this very specific way that you need to word how you reject your null hypothesis. You need to say that you're rejecting it based on the confidence interval, which is so it's based on the alpha value subtracted from 1. And that would be, if, for example, with an alpha value of 5%, we would be 95% confident in our result. And as we reject that null hypothesis, we would then conclude that the alternative hypothesis is true, and therefore we accept that alternative hypothesis. So if the calculated test statistic in reverse does not fall into that area of rejection, then basically the way that we're going to report this is that we actually failed to reject the null hypothesis, okay? So what we're saying here is that there's insufficient evidence to show that the null hypothesis of house prices in Fairfax City being higher than the house prices across the state of Virginia is actually false at the 95% confidence level. So in other words, if the calculated stat is larger than the magnitude of the critical value, then we reject the null hypothesis, okay? So I'll show you how we do this very shortly when we get into the actual tests. But basically, imagine that we had a value that landed above these delineation areas, and that's the point that we would reject the null hypothesis. The key point is that we say here that we reject the null hypothesis, or we fail to reject the null hypothesis based on what we have tested here, but we basically never say that the null hypothesis is proven as true. It's just that there's not enough evidence to reject the null hypothesis, okay? So we're just saying that this is kind of the status quo. We're only focusing on that one explicit alternative hypothesis that we're testing, okay? And if we can't accept that hypothesis, then basically we just don't have enough evidence to reject the null. So you need to think through how I'm talking about this and actually remember how to report it for your homework. And also, I think that the book will probably pick up a discussion of how you make these decisions. So look, that's the hypothesis testing process. Let's focus now on a couple of tests. So in a one sample test, essentially this is where we take a single sample and we compare that single sample statistic to a population parameter to determine if it's just selected at random or if it's significantly different. Okay, so we often assume some sort of population parameter using past studies. So for example, let's say we go out and we look on Zillow at all of the house prices in Virginia, and we get an understanding of what the mean house price is based on Virginia, and then we say, well, is the average for Fairfax City significantly different from this mean average that we have, okay? So what do we actually do in the test? Well, the one sample difference of means test basically has this objective that we want to compare the sample that we obtain, for example, house prices in Fairfax, to a population mean. Let's say it's the house prices for the whole of the state. Now, I mentioned before that we have these assumptions that we need to actually meet. So we actually need to adhere to these assumptions, and essentially that's what I call requirements here. So we basically need to make sure that we are randomly sampling, so that we have an equal distribution of probability for selecting each of those items that are within our sample. We also need to make sure that the population has a normal distribution. We also need to make sure that we're using interval or ratio data here, okay? Now, then we need to actually state our hypothesis. So for the null hypothesis, that would be where the mean for the population is equal to the population of the sample. And the alternative hypothesis, the non-directional version, is just basically saying that the mean of the population is not equal to the mean of the sample, okay? And then we can also state directional hypotheses if we think we have an understanding of those. So we might say that, for example, the mean house price in Fairfax we think is higher than the mean house price in the state of Virginia. Okay, and then we can use the test statistic depending on the distribution that we're using. So it's Z if we've got a large sample, or T maybe if we've only got a smaller sample. So here, to get the Z, for example, if we've got a large sample, we're going to subtract the mean of the population from the mean of the sample and divide it by this standard error of the mean that we calculated last week. So that's this sigma x bar value here. And to get that, we just divide the standard deviation by the square root of the number of samples, okay? So let's give you an example. So imagine an energy official from the Department of Energy, DOE, claims that the oil output per well in the US has actually declined since the 1998 level of 11.1 barrels per day. And then the energy official says that, well, this was based on 50 wells that we randomly sampled throughout the US. And the mean output was found to just be 10.7 barrels per day, okay, with a standard deviation of 1.3 barrels between the different wells. Let's test this claim using a 0.1 level of significance. So this is our alpha value, this significance value. And that means because it's 0.1, if we subtract 0.1 from 1, then we're going to have 0.9, which is 90%, and therefore that means that we want to be 90% certain in the claim that's stated here that the actual oil output per well has declined. Okay, so step one is to basically identify the null and the alternative hypothesis. So the null hypothesis is that the mean of the sample is the same as the population, and the alternative is that the mean of the sample is actually below the 1998 level. Okay. Step two, we then basically take the one-tailed, one-sample difference of means test, and we're using the Z distribution, so that's our test, we've identified that. Step three, we identify our alpha value of 0.1, and then basically we would need to identify the point in our distribution where we would have, because this is 0.1, only 0.1%, sorry, 10% of the values lying below that point, and 90% of the values laying above that point, okay? So we can do this in QNorm, we can just give it the value 0.01, and it will basically say that at minus 1.28 standard deviations below the mean, so this is where this line sits here, you have 90% of those values above the mean and 10% of those values below. Sorry, 90% of those values above this point here and 10% of the values below. So now we've got our Z critical value, we can work out the Z value for our sample. So we're going to take based on this this equation here, we're going to take the mean that we have for the population from before, which is 11.1, subtract it from the 10.7 that we've got for our sample. So that gets us the numerator, and then basically we divide it by the outcome for this standard error equation, which is the standard deviation, so 1.3 divided by the square root of the number of samples that we've got, which is 50. And then we get this z-value of minus 2.18, which is well below this minus 1.28 critical value level. So that mean is all the way down here in this area where we would reject the null hypothesis. So basically, as the final step, because we've exceeded that level, we can basically reject the null hypothesis at that 90% confidence level that we identified at the start of the test. Okay, so that's basically how we test this claim at this 0.1 level of significance. That was using continuous data. We might also be interested in repeating this test, but specifically for proportional data. So this is a one sample difference of proportions test where we can compare the proportion of a sample to a proportion of a population. The difference here is that we only require random sampling and that the variable basically is actually binary. So I'll explain what we mean by that shortly. We then need to identify our hypotheses. So the null hypothesis is that the row value here for the population is the same as the row value for, so the proportional value for the sample that we've got. The alternative hypothesis in a non-directional way would be that basically the population proportion and the sample proportion are different, they're not equal to each other. Or we could also have a directional hypothesis where we say that the population proportion is either smaller than the sample, or we could say that the population proportion is larger than the sample, okay? And then we have this test statistic, which here is going to be the z-test, okay? So we can get this z by basically subtracting the row value, so the proportion for the population, from the sample proportion p here, and dividing it by this sigma p value, which is the standard error of the proportion. And then basically that's the proportion of the sample multiplied by 1 minus the proportion as the numerator divided by the number of samples that we've got, and then we take the square root of that outcome, okay, to get this denominator here. So let's give you an example for how we do this. It's pretty much the same kind of setup. It's just that we've got a different example here where we're focusing on proportions, and most of the critical values have stayed the same. So there's a Middletown official that wants to know if the proportion of families within Middletown with one or more children under 18 is different from the national trend, okay, for the whole of the United States. A random sample is compiled of 250 Middletown families, and essentially we have 105 of those families which have children under the age of 18, so that's basically 42% of the families. That's 0.42 here as the proportion of families with children under 18. The last census, okay, maybe 10 years ago, showed that 48.6% of the families have children under 18, okay? So the question for the official is Middletown smaller than the national trend? So we need to set up our hypothesis, and the null hypothesis would be that Middletown is basically the same as the national trend, so this value here, the proportion is the same as the national trend proportion. Or the alternative hypothesis would be that the Middletown value is basically less than the national trend, because we're saying, okay, Middletown is going to be smaller. Is Middletown smaller than the national trend? Okay, so is that value smaller than the 0.486 that you have nationally? Obviously, we know we want to do one-tailed, one-sample difference of proportions test here using z, and our alpha value is going to be 0.1, so we're going to want to be 90% confident that our result hasn't just occurred by chance. Obviously, if we want to be 90% confident that the result hasn't just occurred by chance, and we're focusing on the lower part of the distribution, we're going to end up with the same critical value that we used before, where we have basically 10% of the values down here and 90% of the values up here. And that would be at minus 1.28 standard deviations, okay, below the mean. So to get this z value, then what we're going to do is we're going to subtract that national value of 0.486, so the row value, from the 0.42 that we got, so the proportion from the previous sample that's just been taken. And we're going to get that as the numerator, and we're going to then divide it by the square root of, and then we just work our way through that calculation. And essentially what we get is a z-value of minus 2.12, so that's going to be well below our critical value. It's going to be down here in this 10% of values where we would reject the null hypothesis. And therefore we're going to reject the null hypothesis, and we're going to state the confidence level at which we did that. And as we used an alpha value of 0.1, so 10%, we're going to subtract that from either 100 or from 1, depending on which way you're thinking about it. And that means that we would basically be 90% confident that this result hasn't just occurred by chance, okay? So that's the two different tests that we're going to cover this week, but there are some other kind of issues that we just need to be aware of when we're doing this type of classical hypothesis testing. Various things that we need to keep in mind, okay? So I mentioned before that they're the kind of 6 steps that we would go through to do this classical hypothesis testing, but basically in the future what we'll use are p-values, so probability values, okay? And this is where we're basically we're determining the level of significance for the values that we've produced, okay? So hypothesis testing is basically where we compare values at an arbitrary alpha level, which was very useful when it was hard to calculate probabilities of z or t, maybe 100 years ago, and you had to use tables of standard values. But now we use p-values because we're able to calculate this significance very quickly using a computer. So basically the p-value is the probability of a type 1 error occurring, and the probability of getting the z or t statistic actually exceeding that critical value that we just covered by chance in the previous example. So you'll note that I always kind of caveated those outcomes as the probability of something occurring by chance, because we are ultimately dealing with something randomly occurring here. Remember, we're randomly sampling. And the alpha is an arbitrary significance level, okay? Whereas the p-value is actually calculated. So the p-value, so by using this we can essentially skip a lot of that kind of 6-step process, okay? But the reason why we're actually going through this week is because I need you to understand exactly what's happening in that 6 hypothesis testing step approach. So p-values won't mean anything to you if you don't understand what we're going to be doing this week. In this lecture, also within the laboratory session, you need to understand how we basically calculate that critical z-value, and then we get the mean value from our sample and see whether it's above or below that critical value, in order to then understand how we should either reject or accept the hypotheses that we've actually provided. So that means in practice that classical hypothesis testing isn't used very often, and that means that we're probably going to be using p-values for the rest of the module, so this class. So how does p-value testing work? Well, a smaller p-value indicates that the observed statistic is much further away from the null hypothesis, okay? So we might have suggestive but inconclusive evidence if the p-value is 0.15. We might have moderate evidence if it was 0.08. But then as we start to move below this critical 0.05 level, we start to get much more strong and convincing evidence, okay? So we're basically getting beyond the point at which we can be 95% certain that the results didn't just occur randomly by chance, okay? So the p-value of 0.05 indicates if the null hypothesis was actually true. But importantly, obviously, there's a 5% chance that drawing these samples could just occur by random. So we need to remember that. And that 5% chance is basically reflecting our probability of basically producing a type 1 error by accident. So we can compare p-values to a hypothesized alpha value. So we can conduct a test and we can reject the null hypothesis when you get a certain p-value less than, say, 0.1. But you can also use p-values to make more kind of qualitative choices. So you can use that to kind of make a decision about how you maybe carry out future sampling work, or actually in relation to the phenomenon of interest that you're studying. So one-tailed testing, the p-value is basically the probability of getting the calculated statistic, or a more extreme value. In the two-tailed approach, the p-value is basically double the probability of getting the value in a point of the distribution which exceeds those critical value levels, okay, to account for both tails. So issue 1 is that the null hypothesis and the alternative hypothesis have some issues that we need to be aware of. So the null hypothesis is often a statement of established thought. It's kind of the de facto way that we understand the world. The alternative hypothesis is basically the challenging assertion. So it's the new point of view, for example. And that's why we're focusing on it within this piece of research. Maybe it isn't very well studied. Maybe we want to understand if our existing assertions about the world are true or not. And these two hypotheses need to be identified before we even look at any data, okay? So this isn't, you shouldn't formulate this based on the data. That's basically fishing for a result. That's incredibly unethical, okay? And you should definitely not do this. It's very bad scientific practice. You need to basically a priori, so in advance of actually carrying out the study, the assessment, identify what you think the research hypotheses are. And you need to look in the literature at what other people have found before, what does theory say about the thing that you're studying in order to determine what the existing kind of line of thought is, which would be basically used as the null hypothesis. And then you would set your own alternative hypothesis that you would therefore want to test under certain conditions, for example. Issue 2, so the two-sided or one-sided hypothesis problem, or which should it be? Well, again, that's going to very much depend on the context of the problem. So here I've given you essentially the statistical framework for you to work with, but you've not kind of got any directions to how to apply it to your problem of interest, and that's because you kind of have to make those arbitrary choices yourself. And that's why your paper goes out for peer review, or why we review your work to see whether we think you've made sensible choices or not, because your decisions as to how you frame this need to reflect the problem of study, and therefore there's no kind of hard and fast rules for how these statistical tests should be carried out. So a one-sided hypothesis may be used if you've got very strong kind of theoretical or empirical evidence to suggest that you think that this effect works in a particular direction on the distribution. Or maybe you use a two-sided test because maybe you just don't know anything about this phenomenon. Maybe it's not been studied very well. Maybe you're the first person to go somewhere and collect some data to do this, and therefore you're unsure, so you're going to basically use a two-sided approach. Maybe it's going to end up being less precise as a consequence of that, but then if you've got no a priori understanding of this phenomenon, then this is going to be the way that you basically have to approach the problem. Issue 3, so using a hypothesis test. So always report the p-value for the test that you carry out, and then basically you say that there is either strong, moderate, weak, or no evidence against the null hypothesis, because obviously the null hypothesis is the kind of de facto existing understanding that is present within this area of academic study. So you never say that you accept the null hypothesis, because this is already the de facto way for understanding this phenomenon, okay? So think of how a judge will make a verdict, or a jury will make a verdict, and the jury will basically say that you find someone not guilty, okay, rather than being innocent, okay? They're just not guilty for the crime that they've been evaluated for. You don't know if they're actually innocent. You would never, you would never say that just based on the evidence that's present. You don't think that they're guilty. Okay, there could always be more evidence presented which changes that verdict, maybe to an innocent, as maybe to a guilty verdict. Sorry. Issue 4: the number of degrees of freedom does actually affect the test that you carry out. So I've touched on this before, but basically. Remember that you can earn a degree of freedom when you collect each data value, so it increases, and you basically spend a degree of freedom when you estimate each statistical parameter. So if you basically carry out an example where you collect 51 data points on journey to work times, and then you need to calculate the sample mean for the inferential testing of the mean, then the degree of freedom, the number of degrees of freedom will be the samples that you have, which are 51, minus 1, which gives you 50. Okay, so you've got 50 degrees of freedom within the actual data that you've collected. And the way to think about this is that, remember I said before that we were allocating soccer players to different positions on the field, and we're going to start with the strikers, and then we're going to end up in the midfield, and then we're going to end up in the defence. And after you've allocated all of those 10 soccer players, you're only going to have one place that you can then allocate the goalkeeper to, because you've already allocated all of those players out in the field. The last player to be allocated is going to have to be the goalkeeper, and that's why there's no degree of freedom there, and that's why you end up having the sample size minus 1, because the last player that you allocate is not going to have any freedom to go to any other positions. And you need to think of it like this when we're carrying out these statistical tests, okay? This is a good way to kind of think about it, you know, as a metaphor. Issue 5, so far we've just focused on parametric tests using the normal distribution, but often we don't always conform to those assumptions, okay? So we might have data that's not normally distributed, and therefore we can't use a parametric test. And when we get into that situation, we may need to look at other non-parametric tests, which are basically distribution-free approaches. So this doesn't necessarily require interval, ratio data, or a normally distributed set of data. And therefore, we can use this approach. We just need to be aware that there's basically fewer assumptions, and that's good, but it also means that these approaches are basically less robust than using parametric approaches, okay? So if we do end up with non-normally distributed data, what we would do is we might actually downgrade that data so that it forms nominal or ordinal categories, okay? So if the data are nominal or ordinal in the first place, you basically have to run the non-parametric test. But if you're completely sure that you're unable to meet the assumptions of the normally distributed requirements, so for parametric tests, then you could basically downgrade that data, okay? So you go from the continuous data into ordinal, nominal data, and then you run the appropriate parametric test. If you're uncertain, you could actually run both, and by pairing the two tests and the p-values. Okay, so look, I'm going to close off here. You've had the lecture, the 8th lecture for GGS 300, and we basically covered those 6 classical hypothesis testing tests. And we've then given, we've kind of gone over 2 different examples for tests. So one just focusing on continuous means and one focusing on proportions, both one-tailed, one sample difference tests. And then we've also covered a few of the issues associated with these approaches, okay? So I've mentioned that we're going to be using p-values more frequently in the second part of the course, and also I've covered some of the kind of issues associated with how we kind of use these tests, all right? So this has been quite high level, and therefore what we're going to do within the actual the laboratory session in R is that I'm going to kind of give you some very kind of basic examples for how we carry this out in a few lines of code, using pretty much all of the existing tools that we've already covered in previous examples, just a little bit of fitting those examples into those math equations that we covered today. So it shouldn't be too hard, and it should be quite useful for you because we're getting now into some really nice kind of powerful statistical tests, okay? So tune in to the 6th laboratory session, which will follow this, and thanks for tuning in today to this session. It's been good to speak to you again, and I'll look forward to seeing you in the next laboratory session. So have a good day. Thank you very much. Goodbye.